This particular approach is Davies, the first author, in his text. This one. This is the text for this course, right? Just called simply Quantum Mechanics, second edition. Right? So the Davies approach is essentially to use the so-called Doppler Effect. I'll mention briefly what that is. Everyone's familiar with the phenomenon of when a train, so say you're standing close to a railway track and a train passes you. So it approaches you first and then passes you. And imagine I guess you're near a railway crossing, so I think the train is obliged by law, in most countries, to sound the horn, the train's horn. Now, as the train's coming towards you, it's moving towards you. So at each blast, each pulse of the sound of the horn, at each pulse, the train's moved a little closer to you. So the wavelengths of the sound get compressed as the train approaches you, and then the train passes you, and now at each period of the oscillation of the sound, the train's moving away a little bit. So the wavelength of the sound now is getting stretched a little bit. So in terms of your ear, when the wavelength's getting compressed, you'll hear a higher frequency, like the tone of the sound will be higher. And as the train passes you, the wavelength increases, so the frequency goes down, and you will hear that as a lower sound. So effectively what you're hearing will be a higher frequency at first and then a lower frequency. So it just, and now you've all heard this, it sounds like that's the Doppler effect. Now, something similar occurs with light. So if a particle, for example, is moving towards you this way, and then it emits a photon. Now, the particle, let's say, is moving at speed v, little v here. So it's moving towards you. Let's say it's speed v, and it shoots out a photon. The photon will travel at the speed of light by definition, because it is light, right? And its frequency, like if this particle were at rest relative to you, if it were not moving, let's say the photon is shot out at frequency, what is this Greek letter? Mu? Mu. I don't know well enough my Greek alphabet. What is the name of this letter? It's not tau. Gosh, I'm going to have to invent something. Will I call it just frequency V? Well, I just call it the rest frequency, right? So this is your particle, and it's at rest. It's not moving relative to you, and it shoots out a photon whose frequency. I'll just call about the frequency. I won't even mention the letter. So it's the little zero here means that the particle is at rest, right? And that's the frequency that you measure the photon. Okay, but when that particle is moving, you will measure the frequency of the photon as the photon shoots out towards you. You'll measure it at this value, right? Which will be slightly higher than the frequency of the photon if the particle is not moving. But if this particle is moving towards you at speed little v here, then you will measure the frequency of the photon. That, here's the particle, and then suddenly it shoots out a photon, and you'll pick up the speed of that photon. The frequency of that photon as this value, which will be slightly higher than the value when the particle is not moving. Right? So you have this kind of relationship. This is sort of the Doppler formula. Right? Now, to actually measure this this frequency, you'll need a certain amount of time. Now you can't measure it too long because this particle is moving, right? You're using the Doppler effect to actually measure the velocity, the speed here, the v here, of this particle. You're using the Doppler effect to measure the speed of the particle. Right? You're trying to measure this v. That's the whole point of the exercise. You're trying to know what v is. Okay, and to learn what v is, you're measuring the frequency of the photon that's shot out as the particle moves. Right? And you'll need a certain amount of time to measure what that frequency, the frequency of the photon is. And if you can measure that, you can, and you know what that is, and you know what the speed of light is, so you can deduce, you can find what the velocity of the particle is, little v here, right? So so you need a certain amount of time, call it tau, time t here, to measure this frequency of the photon. Okay. Now, if you take a long time, you can measure that frequency very accurately. Okay. But if you do that, the particle is, it's moved somewhere else, and you're not quite sure, where it's moving. So there'll be an uncertainty in the position. So again, a kind of trade-off. You don't want to spend too much time measuring this frequency of the photon shot out. So you want to keep the time you use to measure this frequency fairly short. Otherwise, the particle keeps moving, and you're not quite sure which way it's going. So that would increase your uncertainty in the particle's position. Okay. All right. Now. All right, so the particle's moving like this. It shoots out a photon. Now that photon will have a certain energy, a frequency, and hence a certain momentum. And since conservation of momentum is one of the basic laws of physics, along with conservation of energy and various other conservation laws, when that photon gets shot out with a certain momentum, depending on the frequency, that will have an impact. It will change the momentum of the particle, right? Like if I'm holding a very heavy medicine ball, big heavy thing like this, and I'm standing on very slippery ice. So if I push the medicine ball away from me, there will be a action-reaction that will force me backward. So the medicine ball has a certain momentum going that way, and I'll have a corresponding momentum change going the other way. So there will be so the particle. Well, this here. What is this? This is again h over c. The momentum here. Here's the momentum of the photon. P for the. It's the photon's energy divided by c. So E divided by c. Now the energy of a photon, E, is just hf, right? That's the Einstein-Planck relationship. So f is the frequency. Well, here we're using this letter, Greek letter, for the frequency. So h frequency divided by c, right? Which is here. So that's the momentum of the photon when it gets kicked out, and that. So because of conservation of momentum, the momentum of the particle will change by that much, by the same amount. Okay? Momentum's conserved, and that's sort of like worst case scenario in a sense. If well, that's the change in momentum of the particle. All right. Now let's assume that the particle has mass m, right? Mass m here. So this v here is the change in the velocity, let's say, worst case, of the particle of mass m due to the recoil due to the photon being shot out. Right? That's the momentum of the photon, and this is the velocity, the recoil velocity of the particle, or change in velocity. So it'll be this momentum, and well, you can put the little m, the mass of the particle, over here. So that mv, big V, that's the momentum change, if you like, of the particle. And then hv over c, that's the momentum of your photon, right? So take the m here, take it underneath here, so you get this relationship. All right. Now we're taking time tau to measure this frequency. So in that time, if this is the recoil velocity of the particle due to the photon getting shot out, to use the Doppler effect, then it's possible the particle then can move this distance. It'll be that velocity, which is this, right, times tau in that amount of time. So the distance is just this times tau. So you just add you put it in here. So what is this? Let's interpret this. This is now the distance due to the recoil, but you don't know what direction that this particle has recoiled in, right? So in a sense, this is the uncertainty in the position of the particle due to its recoil from the emission of the photon, right? So this in a sense is your delta x. It's your uncertainty in the position. So now using the same sort of terminology here, where the delta just means a measure of the uncertainty of the position, delta x. So just the same here. So we're interpreting this to be the uncertainty in the position. Okay, so we just rewrite this here. That's our delta x. Now from this relationship here, the uncertainty in the frequency, when you try to measure the frequency, depends inversely on how much time you take to perform that measurement. If you take very little time, your inaccuracy of the frequency measurement really goes up. Okay, so tau here is just 1 over